I'm happy to kick off today with a talk from Duncan Watts of Microsoft Research.
Is there a clock? Is there a timer somewhere? Is there a timer somewhere? Timer. Okay. 10 minutes left. Great. Thanks very much, everybody. It's great to be here. Sorry that I missed yesterday. It sounds like it was an exciting day. I want to talk about some very recent work, hot off the press. This is work from just from this past summer with Abdullah Al-Matouk, who is a PhD student here in the Media Lab working with Sandy Pentland. Actually, no, you're in computational something here at MIT, and he was an intern with us this summer at Microsoft. And Ming Yin, who is also here, who was a postdoc with us at Microsoft Research for the past 2 years and just started at Purdue. And so the motivation for this work is, of course, a large literature and history of researchers in a variety of different fields who are interested in the determinants of team performance. So what is it that makes for a good team in terms of the people that you put together in it? And of course, this is also a question of enormous practical interest, and there are, of course, thousands of companies around in the economy where you have managers and HR departments and senior executives worried about how to optimize team performance. And working for a large company, we hear about this sort of stuff all the time. And you might think that this large literature on the determinants of team performance would be useful to the managers and HR departments. But unfortunately, after several decades of studying team performance, it's a little unclear how you would address the practical problem of who to put in what team for what particular task. And one of the issues here is that there are just lots of things that you might think to measure about individual people and that you might suspect are somehow relevant to their collective performance when you put them together. So of course you might think individual ability, if you increase the average ability of team members, that should help team performance, right? But how about people not being jerks and working well together? So how about something, maybe you might think that social perceptiveness, the ability to understand or empathize with other people or to read other people might be even more important than your absolute level of skill. You might also think that absolute levels are less important than diversity, and there's been a tremendous amount of discussion in the media and certainly in corporate America recently about diversity along many different dimensions, including skill, including cognitive style, including demographics, identity, functional diversity. So you can sort of see already that there's a kind of growing laundry list of attributes that you might think to measure for any given individual. And then the number of ways in which you can combine all of those things to create a team is of course, growing exponentially. So there's a lot of difficulty about even focusing on what to study. And then, of course, if you go look at the literature where people have varied one of these dimensions, even for a single attribute, the results are pretty inconsistent. So some studies find that as you increase individual average ability, team performance goes up. Other studies have found that it doesn't. If you look at skill diversity, some studies find that more skill diversity leads to better team performance. Other studies find the opposite, and other studies find no result at all. The same is true for social perceptiveness. So pretty much anything that you focus on, you can find results that look like these. And so now we're really sort of lost, right? We don't really know, what matters. And even if we pick one thing that we think matters, the literature is not much guidance on how varying that thing will predict or improve the thing that we care about. I won't even get into measures of performance, which are also a little bit of a mess. So one reason we think why this inconsistency exists is really sort of on the task side of the problem, right? That a lot of these experimental studies, and I'm really focusing on experimental studies here today. Of course, there's tons and tons of observational studies. The choice of tasks that the group is working on is somewhat, well, not somewhat, completely ad hoc, and more important than that, inconsistent across studies. So, one set of researchers pick one task that their subjects perform, and another set of researchers pick a different task that their subjects perform, and we sort of have no way of comparing these tasks. Like, we sort of have a sense that they're not the same, but it's difficult to say, well, this task is in some sense, in some well-defined sense, more difficult than this task. And so if we want to think about external validity, we have different sorts of tasks in the economy, and some of them are simpler than others, some of them seem more appropriate for teams than others, but we don't have a very good language for talking about that or ranking things or classifying different sorts of tasks. So I think that's sort of an open area that we're not going to solve today, but we're going to make a start on it. And related to that, it would be nice to be able to vary some attribute, let's say complexity of a task, in some systematic manner, so that you could sort of consistently sample different tasks of the same complexity, and you could also systematically choose tasks of increasing or decreasing complexity. Another problem is that we talk about ability, but typically we measure it indirectly. So you give people some sort of intelligence test, and then you hope that measure is predictive of their ability on the task that you're actually going to have them do, rather than just testing their ability on that task. And there's a reason for that, which is that experimental time is limited and subject time is limited, so you sort of want to maximize the amount of time that people are spending in the team setting, rather than having everybody do everything twice, first as an individual so that you can get good measurements on them, and second as a team, where of course in the middle you have to do some kind of assignment. So that's sort of a big, it's an onerous exercise for traditional lab style experiments, and so people don't do it. And finally, there are all sorts of problems with assigning people to teams. That if you wanted to test some theory about skill level or skill diversity, you would want to first measure everybody's skill independently, or cognitive style, or whatever it is that you think you care about. And then you would like to systematically assign them to teams to test whatever hypothesis you have, right? Rather than just having a bunch of people show up, put them in teams in some other manner, and then try to infer after the fact what their individual skill levels were, right? So that's typically what people are forced to do, but it removes a lot of control from the experimenter. So probably what I think is the most important contribution here is the design of this experiment. Well, whatever. I think all of these three things are important contributions. I'm not going to try to. The first one was my idea, so. So really, it's to get a firmer grip both on the measurement of individual attributes and on the assignment problem. We do really two experiments. We call them two phases, but they're actually two completely separate experiments with the same subject pool. So in the first experiment, everybody arrives and they do the task on their own, or they actually do several tasks on their own, and we measure everything that we can think of measuring or that we care about. And then there's a delay of a few days, and then we randomly or block randomize using the block randomized assignment. We assign people to teams in a second phase where the teams are constructed according to certain treatments that I'll show you, and then we measure their performance as a team on different instances of the same tasks. Okay, so they're not doing the same thing again. They can't just memorize what they did last time, but these are comparable tasks. The second thing we do is we can vary the complexity of the task. So we can go from things that are pretty trivial to things that are basically impossible for individual people to do in the allocated time. And third, we exploit the power of virtual labs to basically do this at all, right? This is something that would be, I think, impossible to do in a physical lab, just logistically, given the number of participants and this requirement to have them come back twice and to do all of this allocation in the meantime. So what's this task that I keep talking about? We're going to study, and before you comment on this, I will concede that this is also a little bit of an ad hoc selection of a task, but we had to start somewhere. So we are choosing what is called a constraint, satisfaction, and optimization problem. So an example of this, the one that we're going to study, is you're assigning students, people, to rooms, okay? And each student has some utility for each room, so there's preferences over the rooms. You're trying to maximize that, but there are also constraints where some students really want to be in the same room together and other students really don't want to be in the same room together or don't even want to be next door to each other. And so you have to satisfy all of those constraints while trying to optimize the task. So you can see this sounds like a complex task, and clearly depending on the number of students and the number of rooms and the number of constraints, you can make it more or less complex in a fairly not as systematic manner as we would like, but a pretty systematic manner. And this, this is an artificial task, but it's not unlike a lot of other kinds of resource allocation tasks that we have to solve in the real world, which is why there's a literature on this in theoretical computer science. We can generate pretty easily tasks of comparable complexity, and we can certainly vary complexity in well-defined ways. So this is what the task looks like, and this is phase one, where people show up and participate as individuals. And this is a graphical user interface here where you can just drag and drop students into rooms, and it will update your score, and the timer counts down to 0. This is an easy version of the task where you have 6 students and 4 rooms. You see the payoffs are in the bottom left-hand corner, and in the bottom right corner, there are the constraints that you have to satisfy. Now we can make that task harder. So we have more students, more rooms, more constraints, and then we can make it really hard. So this is, I don't know if this is the most ridiculously hard problem, but I mean, this one looks pretty hard, right? Like if you had someone, I just gave you that right now and said, go, it might take you 10 minutes to actually sort through all of those constraints, or even sort of to figure out how you were going to go about the problem. Okay, so that's phase one. In addition to that, we couldn't, that's 10 minutes left or 10 minutes? Okay. There's no sort of equivalent, we don't know of a way to measure social perceptiveness on a task, especially when people are performing it individually, but there's a very standard way of measuring social perceptiveness, which is called the reading the mind from the eye test. So you look at a bunch of pictures like this, and you have to say what emotion is this person expressing. And so this is a task that has been done thousands and thousands of times, and there's a fair bit of inter-rater reliability here. So we're reasonably confident that this is measuring the thing that we care about. So that's phase one. So they do 5 of these tasks of different difficulty, complexity. They do the reading the mind and the eyes test. They answer some other questions that we ask them about their cognitive style. And then we get all of those results, and then we invite them back a few days later. And this time, we randomly assign them to blocks. Right? So we have a bunch of different treatments that are, so 12 different treatments, 6 team treatments and 6 individual treatments. And so some people come back again and perform again as individuals, because we want to be able to compare individuals to teams on the same tasks. But almost 600 of them are assigned to teams where we allocate some to low ability, mixed ability, and high ability. So we are testing for skill diversity here, and the other half is low EQ and high EQ. So EQ is social perceptiveness, emotional intelligence quotient. Okay, so phase 2 looks very similar, except now you can see there are these little icons up in the top right-hand corner which show you and your teammates. So there's now teams of 3, and there's a chat box over on the right-hand side, so you can talk to each other about, you can order each other around, you can argue about things, you can collaborate, you can do whatever you want. There's no rules about that. But the UI only allows one person to move an icon at a time, so we sort of avoid a bunch of conflicts, but basically if somebody else is doing something, you can't do that same thing. Okay. So this is a representation or schematic of the entire experiment. You can see we start with 5 tasks. We then classify people according to skill and social perceptiveness. We then randomly assign them to these blocks, and then we run them through another 5 tasks. Okay. So just to make sure that we're measuring the right thing, if this is on the left, the left y-axis is normalized score, which is the percent of your maximum score that you could get for that task, and the right-hand side is the duration. And you can see that these are doing the right things, that just averaged over all the teams and all the individuals in phase 2, as you make the task more difficult, people get lower scores and they take longer to complete. Okay, so we're just sort of checking that the thing that we're manipulating is doing what we think it's doing. We also pre-registered a bunch of, we didn't have hypotheses or directional hypotheses because of all of the conflicting results. We didn't know which way things were going to go, so we didn't write those down. We just registered the questions that we're going to answer. One question about comparing teams to individuals, one set of questions about comparing teams to individuals, one set of questions about what predicts team performance, and then also looking at the interaction with task complexity. So just very quickly, I'm running out of time. Performance here, we have 3 ways of measuring it. 2 of them were pre-registered, 1 of them not. So we're really going to focus on just measuring the score and duration, but I'll show you some efficiency results anyway, because one of them is interesting. And then comparable individuals, we have basically 3 ways of measuring, of comparing people to individuals. One is just an average of individuals, and then 2 types of nominal teams, which is sort of the standard way of doing this in the teams literature. One is to randomly pick 3 people and just use the best person's score, where the best person was identified in phase 1. And the most sort of generous type of nominal team is you randomly have 3 people do it. You have 3 people do the task independently, and then whoever does best on that task is the one that you use. Okay. So we find, so the teams line is the green one. You can see that they beat just average individuals, but they don't beat nominal teams. This is actually a very, very common result in the teams literature that people find over and over again, that real teams often underperform nominal teams, which you might think, why do we have teams at all? That was a question that we asked. But this is certainly a very standard result. Interestingly, real teams are faster than all the other combinations for the hardest tasks. And this is something that we're looking into, but we think that this has to do with certain individuals are just more impatient than others, and they sort of badger their colleagues into finishing early. The sort of good enough is, near enough is good enough type approach, rather than sort of hanging around trying to scrape together the last few points. We've done well enough, let's just finish and get on to the next task. And so this shows up when we take the ratio of these 2 things, which we're calling efficiency, and you can see by that measure, real teams do in fact perform better than nominal teams on the hardest task. So there's some evidence that the teams are doing something useful. Now just comparing teams with each other, no real effects here of task complexity, which is, we were sort of hoping to find effects of task complexity, but in some sense this is a good result because it means that things are robust, that you're not sort of finding very different things when you change the task a little bit. So basically skill matters, right? That you put the best people in the team, they do better. This is sort of a very old result. Maybe this is the common sense result that you might have thought was true before you read all this literature about everything else that's supposed to matter more, but it turns out skill really matters. Also, social perceptiveness really matters. Not as much as skill, but a lot. And interestingly, skill diversity has a negative effect. So this is inconsistent with a very, very widely cited set of papers by Hong and Page, who really got sort of Scott Page really got the diversity debate sort of into the public minds with a wonderful book on this about a decade ago. But this particular result doesn't seem to hold up. It is consistent with other work by Baharami, published in Science back in 2010, where he claims that in fact skill diversity is bad. Okay, so what do we find? Here's the questions that we pre-registered. I'll put in a brief plug for pre-registration here. It has, in addition to sort of being the right thing to do, it also really helps clarify what you're going to do before you do it. It's a pain to write these things, but it really, as you work through it, you realize that there's stuff that you hadn't quite sorted out in your own head, and this forces you to do it. Secondly, it really helps with the analysis afterwards, because you think, okay, what are we going to look for? You just go look at your pre-registration and do the thing that you said you were going to do. So it definitely speeds up the analysis at the end. Just very quickly, ongoing work. We didn't pre-register everything. There's a lot of stuff that, of course, now we think would have been an interesting thing to look at, or that we weren't able to include in our design because it was just too many treatments. And one of those is cognitive style diversity. And part of the problem there is, like, we don't know how to measure cognitive style, or rather we can think of lots of ways of measuring cognitive style. So we're just sort of systematically going through and trying all of those. And so far, not seeing a big effect. But this is something that we have to sharpen up and of course, pre-register for the next study, where we hope to test it. And then there's lots of variations, of course, that you can immediately think of, some of which we're going to try in the future. And finally, we'd like to redo everything for different tasks, so we can start to see how do these findings generalize or not across different task types. And then finally, I will put in a plug for Abdullah's amazing software platform, Empirica, which is what allowed us to do this, or what allowed him to do this incredible experiment with 1,200 subjects, which by the way, we began talking about the experiment at the beginning of the summer, and 3 months later, he had run this experiment, right, which is, as far as I'm aware, the largest and most complicated virtual lab experiment that I've ever heard of. Aside from all of his hard work, this platform is what allowed him to do it. So if you're interested in doing team-based virtual lab experiments, I think you should definitely have a look at Empirica and talk to Abdullah, because the hope is we can build a community of people using this platform to do these types of experiments, so that we can really generate some cumulative science. Thank you.
So we'll take some more questions from Duncan when we reconvene after Josh talks. So. Yeah. So our
Good.
Yeah.
Start a timer. Great, thanks. So I'm going to talk about a series of projects that involve a much larger cast of characters. You can sort of see their pictures on the bottom left here. Mike Callan, Jake Shapiro, Tarek, Neil, Joshua, Gabe, and Rob. And before jumping in, I think it's worth, blanking my screen, motivating a little bit, because the context that this research is in is a little bit different than the context of a lot of the papers that have been presented so far. And it's one of very extreme data scarcity. So if you can read the small numbers on this table, it's just a few cherry-picked examples highlighting how long it's been since there's been a full national census in a selection of developing countries. And to give you a sense of like what that means in practice, you can see, so this is Angola, where it was 44 years between successive rounds of censuses, and you can see just how much the population changed. So not only was there a very destructive civil war, there was mass demographic transition, internal and international migration, and the total population increased by about 350%. And so why do these matter? So there was this quote by Kofi Annan, the former Secretary General of the UN, just a few months before he passed away, that highlights 3 key applications that I'll come back to. One is like targeting resources. The second is policy monitoring and evaluation. And then the third is tracking accountability. And he makes this really good point that data matters not just as an input to these decisions, but it actually like brings with it an imperative to do something. Or as he says, fine-grained insight brings tremendous responsibility to act. And so what sort of data is he talking about? The traditional data that people use in development, research, and policy is like survey-based household face-to-face data collection. And when we're talking about measuring welfare and well-being, the first bullet is sort of the traditional gold standard. In developed countries, it would be something along the lines of income or wealth, and in developing countries, typically you rely more on consumption and expenditures because income is largely informal. And then there's a whole literature on alternative measures of well-being. But whatever you're doing, it's very resource intensive to collect these data. So living standard measurement survey, which is truly the gold standard in development, an enumerator will spend literally 2 to 3 days with a single household. And when you want to do this at scale, it costs order $50 million to get a nationally representative household survey. And that's talking like 10,000, 15,000 households, not a full census, which can cost upwards of billions of dollars. So when it's this expensive and this sort of logistically challenging, it's maybe not as surprising that you see a lot of countries which have limited technocratic ability collecting surveys every decade or less. And so what I'm going to start out with is talking about what we can do well. And basically there's been 2 margins that there's been a ton of improvement since like 2014 or so. So this literature has really evolved recently. About using high resolution, basically the 2 sources of digital data that do exist in developing countries, which are remote sensing data like satellite imagery, and then digital trace data, and in particular data from mobile phone networks. So worldwide penetration is like 96%, but even in the poorest countries in the world, you'll see mobile phone penetration in the like 50 to 70% range. And so let me just sort of go through these 2 approaches, like the caricature of these approaches in brief. So approach 1, which I'll call sort of the remote sensing approach, looks something like this, where you'll collect ground truth data. So this little image down here is meant to be the ground truth data. So this would be like regionally aggregated measures of wealth that come from these traditional nationally representative surveys. So you might get a district or a province, or if you're lucky, like a village level measure of wealth. Like the average wealth in that village. And then you match that with some remote sensing data that you can download from the Google Maps API at very fine-grained resolution now. And then throw this into some convolutional neural network or other deep learning model to basically figure out what are the best predictors of wealth from satellite imagery. And then once you have that fitted model, you can generate these like very granular estimates of predicted wealth. So that's sort of the first approach. The second approach is similar but a little bit different. It says instead of doing this at starting at the regional level, let's start at the individual level and like build up regional maps from individual level predictions. And so the idea there is to say, okay, let's start with some data set like this. So this is a data set that I'll come back to of mobile phone activity from Afghanistan. We'll sample individual mobile phone users and go and survey them. So then we have a matched data set where we know for a subsample of people who we have digital trace data, measures of ground truth that we collect in surveys, and then we can fit a model and say, okay, based on phone data, can I predict how wealthy you are? And once we have that fitted model, we can then project out of sample to everyone who uses a phone in the country and generate, again, sort of high resolution maps of predicted wealth and poverty. So this, I would say, is sort of a success story. This is something that at least insofar as we're concerned with estimating at a single point in time the cross-sectional distribution of wealth, we can do this pretty well. And big organizations like the World Bank and the United Nations and national governments are now sort of mobilizing to incorporate these estimates into their statistical operations. So this is like a distant second to going and doing a proper nationally representative household survey. But if you don't have $50 million to throw at that problem, you can do this for $50,000 and a bunch of imagery or phone data. What we can't do, and so I should say, so this is quite useful. I'm going to sort of not talk about these applications as much, but in addition to just generating pretty maps, these maps can be useful inputs into sort of targeting resources. And the use case to have in mind is you have a budget constraint, you're a policymaker, you want to get resources to the people with the highest marginal utility of consumption, and you'd rather use like a pretty map that looked like what I just showed you than census data from 1980. It's not as good as doing a new survey at that time, but it's sort of a stopgap measure. But what we can't do, and I'm happy to be corrected here, but to my knowledge, there's not a single paper out there that does this convincingly, is to be able to estimate dynamically changes in welfare of a population over time. And I'll just pause and say, I think between the two, if I had to choose, the second is the one that's actually much more useful, because the set of use cases that this enables are really much more, in my mind, impactful. You can do disaster response, policy monitoring, and then sort of the holy grail in the development, research, and policy literature, which is policy monitoring and evaluation. In other words, if you want to know which policies are effective or not, typically you need like multiple time snaps of data, like a pre and post observation. Okay, so why is this hard? I think there's a lot of people in this room even who have done work that basically shows something like the following, that when some cataclysmic geopolitical event happens, digital trace data go haywire, right? And I'll show you a video of what this looks like in Rwanda. So this is a video showing you mobile phone traffic on a single day in Rwanda, and each frame in this video is like 1 minute of the day. And then the country is divided into these Voronoi cells, where each cell is the approximate catchment region of one mobile phone tower. And then the cell's red if the normalized call volume's high, and blue if it's low. And at some point in this video, there's an earthquake, and the earthquake strikes, and you'll see that right then, all the call traffic gets concentrated into this one region of the country. And if I go back to the previous slide, you can see over here, this was the epicenter of the earthquake right here. And this is fairly characteristic. There's a lot of papers that show that when these things happen, like you can see it in trace data. And so the question is, well, why can't we just like take these two things and put them together, right? What I showed you earlier is that I can take, say, mobile phone data and at a single point in time build an accurate map of the distribution of wealth and poverty. So why don't I just fit that model, and then maybe I can't collect more ground truth labels, but I'll just hold the model fixed and update the input data, right? And then if we sort of imagine that animated video, we can say, oh, well, we're going to get updated maps of the distribution of wealth. And you're probably all thinking all the reasons why that's bad, but if you go and talk to people at the World Bank, they're like, that's what we're going to do. And so we collected some data to see how well this would hold, and at least with phone data, the performance is like pretty miserable. And I think if there's like one figure to remember from this talk, it's this one. So what I'm showing you on the left figure is, showing you for like one sample of 1,000 labeled data points, if we do cross-validated estimates of the predictive performance at a single point in time. And on the right, I'm holding the model fixed. So we train a model using January data, and then we update data with February and March and June and so forth. And we see how the performance degrades very quickly. So within a couple months, we're basically only explaining 10% of the variation in the wealth of our population. And so I won't really belabor this point, but you can imagine all the reasons why this is not working well. One is just that we're using like inappropriate methods, and we're using stationary machine learning models in a dynamic context. But there's also some like much more fundamental issues that I think are not just like purely technical things that we can necessarily solve. I guess if I had to highlight one or two, maybe I'll highlight the first bullet point, which is that this may just be a fundamentally impossible task, right? If we want to estimate the happiness of a household and how that happiness is changing over time, and we're doing that with satellite imagery, like it may not be the case that you can see from a satellite whether the person in the household is happy. Now, that's fundamentally different from being able to estimate sort of the general equilibrium happiness of that village, which says, you know, on average, happiness is correlated with these things that we can see, like roofing material and road infrastructure and so forth. And so this might just be a fool's errand to try and do. OK, but so what I'll spend the next half of the talk talking about is, so basically everything until now is sort of well established. And what I want to talk about now is what we're doing. And this is very premature. But we just got data back, so we have a lot of work to do. And I think this is a very multidisciplinary audience, so it's a good chance to solicit feedback on what to do and what not to do. So let me talk about the data we're collecting to do this dynamic estimation. What we did is we conducted basically panel surveys with about 1,200 Afghans in 2 provinces. And let me just show you. So here's the map. Up in the top left, you can see a map of Afghanistan. So we went to Kabul and Parwan province and surveyed 1,200 male heads of households. In each household, we went through informed consent procedures and then conducted a face-to-face baseline interview. It took about 2 hours, and then every roughly 3 weeks thereafter, we did a follow-up interview, either some of them on the phone and some of them face-to-face with the same male head of household. And then this provides us sort of standard survey-based data on a variety of measures of well-being, including standard things like income, consumption, and wealth, as well as more sort of speculative measures like subjective well-being, happiness on a Likert scale of 1 to 7. And then there's a detailed module on social and economic shocks experienced in the last 2 weeks, which I'll come back to later. OK, so then we have the survey data. As I mentioned, we connect this to data that we get from the mobile phone operator. So an inclusion criteria in this study is that they have a SIM card on the largest network in Afghanistan who we worked with. And then we can treat this as a standard or quote-unquote standard supervised learning problem, where we're trying to predict some characteristic that we measure in our survey amongst the sample of survey respondents using some flexible non-parametric function of the data we get from the operator. I won't really talk at all about F right now, but if this is something in the Q&A, there's a lot of papers on this. You can just think of it as like applying some method for feature engineering and then layering on that some like gradient boosted prediction model. OK, and so what does it look like? So the starting point is that when we just throw the data into the traditional stationary models, we get the nice traditional stationary results. In other words, the way to read this figure is each dot in this figure is a person wave response. So this is the true wealth as measured in the survey, although quote unquote true. There's a huge amount of classical and non-classical measurement error in things like wealth and well-being. And then on the y-axis, we're plotting the imputed wealth from this machine learning model. And we see a relatively good fit here. And then I don't repeat the figure, but you can have in the back of your head that decline where if we go out of sample or out of time prediction, that R-squared drops from roughly 0.5 to roughly 0.1. And so why is this happening? I think this correlation matrix is maybe like the most immediate way to understand it. What I'm showing you here is, so over the course of this study, I think there's 13 distinct waves, or 14 different waves. In each wave, we can fit a different model that maps wealth and phone, that shows the relationship between wealth and phone use. And what this figure is showing you is basically the correlation between feature importances between those 14 different models. And what we want to see here is a lot of dark blue. And we don't see a lot of that. Because basically what this says is that in any given month in this survey frame, the best predictors of wealth from phone data change quite a bit. And so this maybe provides some indication of why this, this covariate shift is occurring. And so it's not surprising when we try and jump the gun and do the thing that we set out to do at the very beginning and take the variation in phone data to predict week-on-week changes in self-reported welfare from this population that we don't do very well. Now, I should say, this is a hard task, right? If predicting stationary wealth or stationary happiness is hard, predicting changes in wealth or happiness are even harder because in any given 2-week period, there's not a lot of signal. There's not a lot of change in the wealth experienced by a household. And there might not be a lot of change in the wealth, in the happiness of a household beyond just sort of measurement error. So that's sort of the discouraging news. What's more encouraging is, and probably what we'll end up writing this paper on, is, at least this first paper, is about predicting these idiosyncratic shocks. And so there is a tiny little bit of experimentation in this project, which is the following. So mostly the data collection exercise was just that. It was designed to grab a bunch of data that would allow us to do this dynamic measurement inference. But we also layered on an RCT where each of the subjects in this study at some unannounced point received a randomized gift. And the value of the gift was, so everyone, the control group got sort of an in-kind gift, which is a nice bag of tea in this fancy plastic bag. And then the treated groups got that as well as a cash bonus. And so the cash bonus was either small, equivalent to about 1 day's worth of wages, or large, equivalent to about 2 weeks of wages. And so this creates like an exogenous positive economic shock for at least 2/3 of the population. And then more endogenously, we observe, this is Afghanistan. There's all sorts, actually, I'll show you a slide in a second, of negative idiosyncratic shocks that are experienced by this population, some of which might be sort of exogenous, like violent events. Others are clearly endogenous, like a birth or a wedding or something like that. And this is a little hard to read this figure, but the takeaway here is that in any given survey, roughly 30% of the households surveyed report experiencing at least one significant negative economic shock, which is very unfortunate, but also creates a lot of signal for this dynamic inference. And if you look at the trace data, so the phone data, we see very clear signals similar to that animation I showed you earlier, that at the individual household level, you see individual household responses to idiosyncratic shocks. So not just covariate geopolitical shocks, but shocks that are just experienced by single households. We see, so what this figure is showing you is each row in this is a coefficient estimate from this sort of fixed effect regression that tells us the effect of each of those different shocks on, in this case, the average call duration. So what we take away from this, like the arrow is pointing, is saying that in the weeks after this positive income shock, the average length of a call made by the people affected by that shock goes up slightly. And down here, I guess, in weeks when they report lower than expected crop yields, they tend to make slightly shorter calls. And we can produce literally thousands of these figures, one for every possible feature or metric of phone use that we estimate. This one I cherry-picked because I think it's counterintuitive. This is showing you how the balance of calls responds to shocks, where balance of calls is the ratio of outgoing calls relative to total calls. And in general, that's a positive predictor of wealth, because in most developing countries, only the caller pays the cost of a phone call. You don't pay to receive incoming calls. But what we see here is that after people get these gifts of 1 day or 2 weeks of wages, they actually initiate fewer calls. And now, ex post, we can come up with explanations. There's actually literature on kinship taxes and things that would be consistent with this, but it's certainly not what we expected ex ante. But I think the main takeaway is there's a lot of signal here, and so it should not be surprising that when we take all that signal and roll it into a classification model, we can actually predict fairly well. In this case, this is the ROC curve for predicting that cash transfer, that cash gift, in the confusion matrix. And then over here are the sort of distribution through a bunch of bootstrap simulations of estimating the AUC for the cash drop on the bottom, and then a bunch of other idiosyncratic household shocks above it. Okay, so that's pretty much it. Just to summarize, I think this line of work was and is intended to develop these real-time measures of poverty and vulnerability. It's turned out to be a much harder exercise than we thought. So what we can do well here and then in previous literature is stationary wealth. But as soon as you diverge from stationary towards dynamic, or as soon as you move away from wealth towards other more subjective and variable measures of well-being, it becomes much harder. So basically, that low-hanging fruit that has been established in like 20 papers is truly a low-hanging fruit. Other measures are much harder. And in particular, predicting changes in welfare over time, which I do think is that holy grail is quite difficult. On the other hand, we do see quite a bit of success predicting these positive and negative economic shocks. Okay, so what are we doing now? I think maybe I'll just highlight the third bullet point, which is probably the most exciting, is to actually work with some of these groups that are actually implementing these policy interventions. So the World Food Program is doing a cash transfer program in Haiti where they're giving cash transfers to vulnerable households. And they have their own sort of survey-based data collection to do a program monitoring, which gives us some estimate of the impact of their cash transfers. And so we're trying to see if we don't peek at their data, but we do the same sort of survey data collection pre and post, if we can train a model that how accurate those predictions are relative to the ground truth. And then with Give Directly, they're this great organization you should all know about that sort of directly sends cash to poor households. But the critical problem in their pipeline is identifying which households in primarily sub-Saharan Africa should receive this massive cash influx. It's like $2,000, so it's meant to be a year's subsistence wages. But identifying the poorest households is very hard for them. And so we're trying to see if we horse race satellite versions versus phone versions versus traditional versions, like what the loss is, and if it outweighs the cost savings. OK, I think I will leave off there. I guess there will be an open Q&A, and then please email me if you have ideas for how we can solve these problems. Thanks.
Yeah, so if Duncan, you can join us on stage. Yeah, really, really impressive work. So just I'll maybe kick things off with a first question, and then we'll take questions from the audience. So Josh, I think this point that obviously things are changing, and then this breaks your machine learning model is really relevant. What are some of the cases you've seen from policymakers or other people working in applied spaces where they're kind of, I guess, blind to this fact? Are people going ahead and using these models without doing the more kind of careful analysis and introducing these shocks that you've been doing?
Yeah, I mean, it's sort of a delicate balance, because on the one hand, we're interested in seeing and helping them integrate these sort of different styles of doing measurement and mapping into their operations. On the other hand, we don't want people to start using things that we have no confidence in. And I think there's a big mental leap between sending enumerators into the field, waiting 2 years to get the results, and then informing policy, and doing this immediate satellite-based or phone-based approach. But the leap from that to that sort of cross-sectional exercise to a dynamic exercise is, I think in their eyes, very subtle. And so it's hard to sort of emphasize that this is a use case that has been vetted, and this is a use case that has not. I think there are other examples of, there's the Google flu trends example that's a classic. And so I think those sort of things are helpful when we say, oh, look, you can do this, measure it right now, but if you do this dynamic extrapolation, just be very wary.
Yeah, and just a quick question for Duncan as well. So you had these EQ measures, or this kind of social perception measure. Did you see any traces of those people just behaving differently in interaction with their teammates that might indicate that that was showing up in how they interacted?
Yeah, we also asked people. We did a sort of post-experiment survey where we asked people about their style of solving problems, like sort of how tolerant were they for constraints? Did they would they if they had a complete solution that wasn't optimal, would they just sort of stop and move on to the next task? So we had a bunch of things where we were trying to get at their style of solving problems, and we also asked them about their experience in the team, and we got some very funny or telling responses back where there was this one team in particular where one person scored very low on EQ, and the other two people were complaining about this person, and he was complaining about them because they just didn't get it, and so there were sort of quite interpretable signals that were consistent with the scores that we were getting. So I think, and we haven't looked at this data in any sort of systematic way. These are just sort of little vignettes that Abdullah pulled out of the survey responses, but at least sort of qualitatively, we felt that these scores were really picking up the thing that we were interested in. Yeah.
Cool. Yeah, I was thinking, whether people are clicking on things at the same time or not, if they're how much they're running into each other essentially in this environment. So let's go to Sandy.
Yeah, great talks. So Josh, one of the things that struck me with this is that when you do dynamic things, I think you tend to run into the limits of current machine learning. So, because you're doing things without causal models underneath them. You could look at that as feature engineering. Like if you knew something about the causal structure, you could put specially engineered features in there that sort of go out. Does that sort of fit with your sense of it? I mean, this is also true, a potential interpretation of some of the things that you're doing, Duncan, but let's start with you.
Yeah, absolutely. I mean, I think, and it's also sort of just the limits of my knowledge, but certainly, I teach classes in machine learning, and the classical canon of machine learning models are all stationary, right? They're not really, I mean, there are, and Susan talked about this a little bit yesterday, about contextual bandits and so forth. There are these like adaptive learning approaches that are, coming out that might be appropriate for these sort of models, but certainly like the 98% bulk of models that we teach are not really designed for these dynamic processes where you have a lot of covariate shift and you have a lot of dynamics over time.
Have you considered, taking, I guess, a very dynamic approach to the survey data collection? I mean, it's really great in this Afghanistan field experiment that you have this super regular data, but I would imagine that what you would often want to do is say, something has changed here, maybe we can actively survey that person.
So that's like a top priority. I mean, there was a bullet point on the last slide where I think like one of the outcomes that we see as like a long-term goal is something that resembles like a power calculation for people that want to do this sort of like dynamic inference. Because power calculations are something that development policymakers are very, very comfortable with. And when we go to them with these methods, they ask for like that. They're like, all right, well, we know that there's this standard deviation in our outcome variable. We expect this much variation over time. So like, how many people do we need to survey? And it's also a situation where you can put like a very precise cost on the cost of like sampling. Adding a respondent in Kabul is very different from adding a respondent in Kandahar. And so, it is a situation where we could imagine formalizing that cost function empirically and integrating it into the sort of model that you suggest. We haven't done that, to my knowledge. No one has done that yet, but totally open territory for cool work.
Yep.
Duncan's paper, and so one thing about the task that you have in your experiment, I think this task is super complex, sure, but it's probably not a task which you can very well divide into kind of subtasks. And I think this is probably where teams are getting stronger and better. So is it not perhaps, given that most real-life tasks are divisionable tasks, is it a little bit unfair comparison? Or what was your kind of reason to choose a task which cannot really be divided here?
So you're absolutely right in one sense, and then I'll say something else about some future work that we're hoping to do. So there was a, the constraint that came along with this two-phase design is that you want to have everybody do the task as an individual, right? Because you're going to measure their skill on the task. So now you've got to pick a task that everyone can do as an individual, right? Which is already different from many tasks in the real world, where if you think about, lots of tasks in a business environment, you need software engineers, you need designers, you need marketing people, you need managers, and they all have very different skill sets, and they all solve different parts of the overall problem. And we don't capture that in this environment for various, for that reason, and also, we're recruiting people off Mechanical Turk, so we don't have specialized skills. So we can't do division of labor tasks of the sort that we sort of really do in the real world. But what we can do, and what we intend to do in the future, is scale up the task. So it gets to a point where it's actually so big that no one person can do it, right? And so you have to have some sort of division of labor. Just because I can't do everything, so you do these students and I'll do these students, and we'll sort of do some kind of reconciliation at the end. And we can actually, we didn't do this in this experiment because there's only so many things you can do in one experiment, but in future experiments we can actually force that to happen by designing in distributed information, right? So rather than everybody looking at all of the students and all of the rooms, you just see one chunk of the task and I see a different chunk of the task. Or alternatively, we could see all of the information, but I can only control certain students. So there's a distributed control. So by playing with distributed information and distributed control, I think we can actually start to get to something like the division of labor. Ultimately, of course, in the long run, what would be great would be to do even more realistic, or to do more realistic tasks, recruit people off some of these freelancer websites where they actually do have specialized skills. And I know that Michael Bernstein at Stanford has done some of this sort of work where they're really building real things. They're building real software. They're designing. They're working on design projects or whatever. So I think we can sort of get there eventually. But I certainly agree with the comment, and I think we can do some of it with this task, and other stuff we'll get to eventually. Thanks.
Oh yeah.
Thank you both for your talks. This is a question for Joshua. I'm trying to get a better understanding of the complexity of dynamic predictions. So is it because the underlying phenomenon itself is very highly stochastic in the sense the ground truth is changing in a sort of unpredictable way? Or is it because of the learning algorithm is sort of not powerful enough, if you will, to capture this trend? Or is it sort of both at play?
Yeah, I think the answer is we don't know. I mean, it could be all of the above. There certainly is a lot of, it's about the signal to noise ratio in the dynamics, right? Like I use the example of, we ask people a Likert scale 1 to 7, how happy are you like right now? And there's a lot of idiosyncratic error in measuring that. And so the question is like, is the true signal that we get in week-on-week differences and responses to that, how correlated is that with like the latent happiness that we care about? So that's like one challenge. And then the other challenge is about the data that we're getting to predict that. And it so happens that like in a given 2-week period, the average respondent in our sample makes like 30 phone calls, right? So that's a sparse data set to infer a lot of like variation to predict these sort of features. Now, in the papers that I and others have written in the past, you're working with like a year of phone data to predict like one slice in time in wealth. And there's a lot of reason to think that like wealth, which is somehow a measure of a permanent income, is actually correlated with like a year's worth of dense sort of robust mobile phone use. And if you start to accelerate that into smaller chunks, then it gets difficult. And so, sort of to Sandy's question, you can throw these data at traditional machine learning algorithms. And the sort of things we've done is say, okay, well, if we don't restrict ourselves to just 2 weeks, but we take like the moving average of 6 months, then of course our models do better, but then we're sort of also prone to overfitting because these periods are overlapping. Or similarly, we can take, if we have 13, 14 waves of data, we can expose our models to more waves of data. And certainly they do better, but that's sort of like sidestepping the real issue, which is, I think, the other point you mentioned about like inappropriate models for this like streaming data process, to convert that streaming data function into this like latent state model of welfare as reflected in all of these different survey responses that correlate with welfare.
It seems like also the data that you have is this kind of relational, transactional data, and that when I'm calling somebody, there's somebody that I'm calling. And so I wonder if that's an angle that you've looked at, especially in the response to these shocks, and that whether you could see some of the spreading news of I just got this payout, or maybe I'm not sharing that information, or certainly when people are subject to really negative shocks, that they're reaching out to people.
I think that's a really interesting idea. It's not something we've looked at too explicitly. I will say that, in that F function, we have this feature engineering machinery that basically extracts a bunch of characteristics of a person based on how they use their phone. A lot of those characteristics do capture this intuition. We have the full network graph from the 7 million subscribers. And it's interesting. If you look at, so this is in the prior study where we're trying to predict cross-sectional wealth. We have like 2,000 features that describe a person's social network, their mobility, how they use their phone. And the single best predictor, if you just like compute the unconditional R squared between each of those 2,000 features in this measure of wealth, is like about the entropy of the second-degree network communication. So like it's not about your friends, but it's about their friends and how regularly use their phone. So now, I don't want to read too much into this. It's probably just like overfitting on this single sample. But a lot of the features that tend to pop out as predictors of well-being are about like higher order network structure.
Mm-hmm. Yeah, which certainly could lead us to think about how to help people design some of these networks. Yeah.
Hi, this question is for Duncan. And talking about the idea of multidisciplinary teams and diversity of skill sets that you were talking about in your results. So it's been my personal experience that one of the biggest challenges on a multidisciplinary team is having a common vocabulary such that people, say, in marketing can talk to a data scientist or to advertising, so forth. Did your experiment account for the communication overhead, or is that something you plan to look at in the future?
So the short answer is no, and I'll just say that there are lots of types of diversity, and I think one of the frustrations that I have with the diversity debate right now is people are not being very clear about what everything means, so often when we talk about diversity, we mean demographic diversity, but also often we mean cognitive style diversity, and these things often get conflated. But actually, if you go back and read the original papers that sort of kicked off a lot of this discussion, it's about skill diversity, which is a different kind of diversity again. So that was the one that we focused on. We are now looking at cognitive style diversity, where we measure it both from survey responses and also from direct measurement, behavioral measures. And that's getting closer to the kind of thing that you're talking about. But I think to really get at this question of language and shared vocabulary, which people have, of course, theorized is important for teams, we would need to have a different sample of workers, right? Like everybody's kind of interchangeable right now. If we had a panel of people who, I don't know where we would get them from, but I think there are other panels out there that have more features on the workers than Mechanical Turk does. We could start to systematically put people together who spoke in some sense different languages and see whether that has a positive effect because you're challenging me and you're making me think outside the box, or whatever it is that people can do when they're coming from different perspectives. But also you're taxing me with this stuff that I don't understand, and I would rather just talk to somebody who uses the same words that I use. And so you can imagine that going in either direction as well. And again, we can sort of put that on the map of things to do in the future. But we're starting with a much narrower version of diversity right now. Thank you.
And I know we have some more questions, but I think actually we need to go to break so that then we can start our parallel sessions. So yeah, let's thank the speakers.